team that looked at production of pharmaceutical tablets with soy, and I'm Caitlin Headings.
I'm Somi Nagar. Mark Aikman.
And Drew Andis.
Our project was looking at using soy in pharmaceutical tablet making. So when you have a pharmaceutical tablet, you have your active ingredient, which is the actual drug molecule, and then you have a lot of different excipients that do other functions within the pill. The highest volume excipient that's used in tablets is the binder or filler, and so that's what we wanted to replace with some sort of soy product. So just a little background into the industry right now. Microcrystalline cellulose, or MCC, is currently the most commonly used binder in the pharmaceutical industry, and so that's the kind of baseline that we wanted to compare our results to make sure we were matching up with the properties of that compound. Also, there's been some previous research done in the ABE department here that's shown that using soy derivatives in tablets has lowered the tensile strength of the pill, meaning that they'll break easy. And so that's something we wanted to look at fixing with our soy product. And those studies showed that soy protein concentrates are the compounds that had the highest tensile strength within those. So kind of looking at all of that, we made our objectives here for the project. You can see they're outlined on our poster. And since the previous research showed that soy protein concentrates had the highest tensile strength within the tablets in the past, we wanted to start with using a soy protein isolate compound as our binder or filler. And then we wanted to find some way that we could process that soy product so that it would end up with tablets that were stronger. And so we were going to look at maybe extruding that and then looking at kind of the effective oil content within that to see how strong our tablets are. And then once we figured all that out, we wanted to scale it up to an industrial size process.
So we started off doing some small laboratory scale tests to kind of figure out what we wanted to do with our large scale processing. So the three main variables we looked at were the oil concentration, the oil content in our tablet, the extrusion, if we would extrude the powder or we would leave it as a powder, and the compaction force used to make the tablet. So what you're looking for in a good tablet is a high breaking force, a high force used required to break the tablet, so that it stays compact in the package and doesn't fall apart when it's being forever. So what we looked at was our oil content, and with our oil content we proved that if you add oil, it lowers the breaking force and it's not good for our tablet. With our extruded product, that proved to have a much higher tensile strength and give us a higher breaking force, which is what we were looking for. We also compared our tablet to the industry standard MCC that Caleb had talked about, and our tablet was slightly less than the industry standard, but it still measures up to it and could possibly be used for actual tablet making.
So the next large portion of our project was to actually scale up everything that we had done and create a process and plant design. And so if you look here, this is a typical pharmaceutical tableting process with the exception of the extrusion. And the extrusion for us serves the purpose of reducing the size of the particles of soy protein isolate. And so when we do that, we think that we're just fragmenting the proteins that are in the soy. And so after that, you're drying, you're grinding, you're mixing things in along the way. The drum dryer for us serves as a roller compactor, and that simply creates covalent bonds between the active pharmaceutical ingredient and the filler itself, or the soy protein isolate. For us, alternative solutions that we looked at were wet granulation. That simply keeps more moisture in the process along the way. You use, for the most part, the same machinery. And then some other things that we could have done, we could have changed the roller compactor to a granulator. It's just a different type of machine. And then a tray dryer switched to a spray dryer, which is also common in industry. And finally, we just have a picture of our actual plant design there. That's fairly typical as well in the pharmaceutical industry.
And because everything costs money, I'm going to be going over the economic analysis here. You can see the breakdown right here. We've spent about a little bit over $7 million on this project. In fictional money, it's not real money. So you can see that our break-even point is about 5 years, and that means that it takes us about 5 years to make back what we spent. Our return on investment is about 20%.
You can see down here the breakdown of our annual raw material costs between the binders, the fillers, and the lubricants. And there's also an equipment breakdown right here, and you can see that the tablet press costs the most money. This does have an impact on Indiana. The impact and sustainability section is right here, and you can see that per year there's about 1,200 acres of soy that we would need in order to make our process or our product, and that's about 9 to 10 Indiana soy farms. And that's really good because there's about 40,000 soy farms in Indiana. And this is also going to reduce the soybean surplus, which means that we're going to have a lot less waste. And if we draw out of that surplus, that means that we can basically get the material that we need in order to make the process. In terms of sustainability, we're going to be reducing the carbon footprint by having the plant in Indiana itself, so that cuts down on transportation costs. We'll be doing things like recycling air streams and using condensers in order to recycle water, and so that'll also cut down on usage of materials.
Okay, so can you tell me a little bit about why the formation of covalent bonds between the pharmaceutical active ingredient and the excipient like MCC or your protein powder is so important in formulating a pill?
So there's really a couple reasons why that would be important. One reason that would be important is when you take the pill, you don't want all of your product to dissolve at one time. So that kind of slows the release within your stomach or your intestine. Another reason is that you don't want the pill actually falling apart before we actually get it to the consumer within the bottle that it's been given in. And then a final reason is that you don't want the API just binding to the API and the filler binding to the filler. You want them to bind to each other, and we do that using the roller compactor of the granulator.